Kenichi Soga, the Donald H. McLaughlin Professor of Mineral Engineering and Distinguished Professor of Civil and Environmental Engineering at the University of California in Berkeley. The title of his lecture is From Geo-monitor to Geo-adapt, Leveraging Distributed Sensing and Data Analytics for Performance-Based Design, Construction and Maintenance. I now call upon Professor Malcolm Bolton of the University of Cambridge to formally introduce the lecturer.
When appointing a new academic colleague, there are a few essential attributes that one should look for. Have they an interesting story to tell? When asked a question, can they organize their thoughts quickly and answer clearly? Do they know the scholarly essentials of their discipline, and can they teach them? At a more strategic level, our previous head of department at Cambridge, Anne Dowling, spoke of the search for the T-shaped academic, somebody with strong roots in a recognized discipline, who was beginning to grow a strong stem of new knowledge, but also someone who showed signs of branching out to connect with other disciplines and to address unexplored challenges. I met Kenichi for the first time when he applied for the vacant lectureship at Cambridge in 1994. He had bachelor's and master's degrees from Kyoto University, focusing on geotechnical and geo-environmental engineering, with Koichi Akai and Masashi Kamon as advisors, and a dissertation on long-term consolidation behavior of Osaka diluvial clay, followed by a PhD from University of California, Berkeley, with a dissertation on mechanical behavior and constitutive modeling of natural structured soils, overseen by Jim Mitchell. Then he'd served a few months as a research fellow at Berkeley, working on FE modeling of soils with Jonathan Bray. So, he presented as someone experienced in soil testing, with constitutive and numerical modeling, and with exceptionally strong recommendations from top-flight advisors. 1 year after his PhD, he was a joint author on only 2 journal papers and 1 paper to the 10th European Conference. But his research presentation in Cambridge was very impressive, carefully and persistently explaining to Andrew Schofield why original CAM clay was inadequate for his purposes. He was equally lively at interview, so we appointed him. It proved to be a really good appointment. In 22 years at Cambridge, he did substantial work on soil anisotropy, structure, creep and aging, and on numerical modeling, as might have been anticipated. But he also worked on ground investigation, contaminant migration, bentonite cut-off walls, tunneling, compensation grouting, methane hydrates, microbial carbonate precipitation in soils, multi-phase modeling of granular flows on saturated soils, pile reuse, energy piles, ground source heat pump systems, and deep geothermal energy. Of even greater significance to tonight's lecture, he also began to work on distributed optical fiber strain sensing, wireless sensor networks, and the detection and monitoring of damage in tunnels based on computer vision, all of which involve collaborating with companies under the aegis of the Cambridge Centre for Smart Infrastructure and Construction, founded by Robert Mayer. How T-shaped is that? He was made a full professor in 2007. Kenichi was simply a powerhouse, often with graduate students waiting for their appointments 8 a.m. to 7 p.m. His international recognition quickly grew, with his winning the Jennings Award of South African Institute of Civil Engineers twice, the Schofield Award of IJPMG, the Walter Huber Prize of American Society of Civil Engineers, and the Telford Gold Medal, and the Russell Crampton Prize, and the George Stephenson Medal of our own institution here. And to demonstrate that ambition in research needn't detract from excellence in teaching, in 2012 he was chosen by the students as the best lecturer in the Department of Engineering at Cambridge. Amongst many other honours, he was elected Fellow of the Royal Academy of Engineering in 2013. In 2016, Kenichi decided to return to his alma mater and accepted the post of Chancellor's Professor in the Department of Civil and Environmental Engineering at Berkeley. His research trajectory has continued, with further research on the material point method of numerical analysis, of large deformations especially. In 2021, he became the founding director of the Berkeley Center for Smart Infrastructure, pursuing further research with his colleagues and students on distributed fiber optic sensing, dynamic traffic sensing, and the resilience of critical infrastructure. We're about to hear more of this. Kenichi also co-authored new editions of Jim Mitchell's rather wonderful textbook, Fundamentals of Soil Behavior, of which the fourth edition is also co-authored by Catherine O'Sullivan, and this is due out in the summer. He's become a fellow of ASCE, an international fellow of the Engineering Academy of Japan, and a member of the US Academy of Engineering. Kenichi's given scores of keynotes and special lectures around the world. He gave the Geotechnical lecture to the BGA in 2007, the Skempton lecture to the 2015 European Conference, the 9th LUM lecture in 2016 in Hong Kong, among many more. But if you haven't previously had the pleasure of seeing him in action, you now have that opportunity. Please welcome Kenichi Soga, your Rankine lecturer for this evening.
Okay. I think I need help from my colleague. I'm sorry.
Could we get some assistance, please?
Yeah, can you make this smaller? I'll show you do that. This is so big. Yeah, sorry. to reduce the text size. Sorry, reduce the text size. Well, maybe let me start.
Does that make
Professor Bolton, thank you very much for your kind introduction. I feel very honored to have you at the beginning of my lecture. Are you hearing me okay? All right, okay. First of all, I'd like to thank the British Geotechnical Association, led by Dr. Andrew Whitley, to having me here. Dr. Chuan Lee of Imperial College made various arrangements for me to be here, and I very much appreciate his assistance. It's been more than 9 years since I moved from Cambridge to Berkeley, and I'm very happy to be back again. And then also, I'm very happy to be back again, and then, to my surprise, my London Oyster card still worked. So at least London Underground hasn't really forgotten me. Thank you so much. And thank you very much all for coming to this particular talk. The title of my talk is From Geo-monitor to Geo-adapt. Okay, so now it's working, so thank you very much. I'd like to start by introducing a challenge that we have in our infrastructure system. We often design our infrastructure with a lifetime of 100 years. But some of our infrastructure have already exceeded this, and many of our infrastructure owners are increasingly looking to extend the life of their assets. At the same time, when we look at the demand side, the world around us is constantly evolving. If we consider London, the activities, environment, and social needs today are different from 30 years ago. And looking 30 years ahead, London will be probably different. This means that when we talk about aging infrastructure, we are not only referring to degradation materials, but also to changes in usage patterns, environmental conditions, and climate. Given these uncertainties, infrastructure can be designed to be adaptive rather than assumed to be rather simply static. The key is to actually understand the actual performance of our infrastructure. Emerging technologies such as advanced sensors and data analytics now allows us to monitor infrastructure better, which provides deeper insights into our system, how it truly behaves. In summary, we may have to embrace that our 100 years design life concept may not be compatible with the actual demand in the future. This means that we can think about making our infrastructure adaptive to change. Let's imagine a world where future generations no longer have to worry about aging infrastructure. In this presentation, I'll discuss emerging technologies. As illustrated here, the adoption of new technologies follows a trajectory known as the Gartner hype cycle. On this graph, the vertical axis is expectation. Horizontal axis is the progression of technology adoption. Many of you are already familiar with some technologies such as building information modeling, LiDAR, wireless sensor network, and so on. Currently, perhaps, artificial intelligence, machine learning, augmented reality are enjoying their peak. I have some new emerging technologies, like what I call socio-technical digital trend. One concern in California is wildfire management. Our recent research, we integrate wildfire simulations with traffic simulation. The two are linked through a social science model that accounts for organizational behavioral responses and public communication during emergency. One of the technology I'm going to discuss today is a distributed fiber optic sensing, which I joined the hype at some years ago. I believe now it's moving toward practical adoption. However, whether it continues to along this trajectory or fades away will depend on the value it can provide. And I'll try my best to show its value today. Today's focus is geotechnical monitoring for detecting movements. We now employ technologies such as computer vision, LiDAR, UAV to capture infrastructure movement. We also began using satellite-based monitoring. The development of wireless sensor network is in the past decade has been provided significant opportunities for us to continuously monitor geotechnical structures, particularly in remote and difficult to access locations. Later in this presentation, I'll discuss the potential role of distributed fiber optic sensing. The key takeaway from this slide is range of precision offered by this technology. Data accuracy varies from 10 to 20 millimeters using satellite measurements to sub-millimeters, less than 0.1 millimeter, with camera-based and fiber optic sensing technologies. As a geotechnical engineer, this level of precision is essential for us to make informed engineering decisions. For me, distributed sensing refers to measurement that distribute across space, time, and multiple sensors. The slide illustrates the spatial variation captured by different sensing technologies like satellites, UAVs, and sensors at local scale. It demonstrates how these technologies enable infrastructure monitoring across various spatial scales. During my time at Cambridge, we worked on developing wireless sensor network system. Over time, this technology has evolved to support large mesh networks. These networks can achieve hopping distance of over kilometers, enabling spatial coverage through multiple interconnected wireless sensor networks, as well as creating redundancy to the system. One of the most significant achievements made in wireless sensor technology is power efficiency, which enables data collection over varying time intervals. For certain measurements, a low sampling rate is sufficient. With current technology, if readings are taken once every hour, the batteries such as these can sustain monitoring for 20 to 25 years without changing them. However, some measurements, like shown over here, such as acceleration, noise, require high-frequency data collection, especially during crucial times. Since the large volume of data is generated, these batteries cannot sustain continuous signal transmission for a long period. The key innovation lies in the ability to trigger data collection only when necessary. This optimizes power consumption while ensures crucial data is captured when needed. Sensors can be strategically distributed within a system to capture detailed and continuous data. For example, the Stirling machine is equipped with numerous sensors that records hundreds to thousands of data variables every few seconds. As the machine advances by just a few millimeters, it generates a lot of vast data sets. It provides valuable real-time insights into its operation and performance. Traditionally, the infrastructure design and maintenance rely on safety margins to account for uncertainties. In this graph, vertical axis presents performance, while the horizontal axis represents time. Infrastructure performance naturally fluctuates. Some days are good, some days are not good, like us. In this conventional approach, we establish performance thresholds based on statistical distribution or engineering experience. However, in some cases, accident may happen and performance unexpectedly falls below the defined limit. When this happens, we recalibrate the threshold. Sometimes accident may still occur due to previous unidentified mechanisms, requiring further adjustments to these limits. In the past, continuous infrastructure monitoring was very expensive. However, with the advances in sensing technology, continuous monitoring is now becoming economically feasible. With new sensor technologies and data analytics, we can now continuously measure and assess infrastructure performance. In psychology, this approach is known as managing safety through everyday work. If we know the actual performance, we can learn how to react quickly if an event begins to unfold. We can manage future unknown demands by reducing unknown risks. We can identify potential improvements in the design and construction processes. From a circular economy perspective, having knowledge of material performance enables resource conservation, component reuse, and sustainable design. This slide highlights the origin of my work in the field of sensing. My journey began under the influence of late Clive Dalton, who guided me how to measure geotechnical properties in situ. Many of you are familiar with the self-boring pressure meter that was invented by Clive. Early in my career, I worked with data analysis related to self-boring pressure meter, and then developed a self-boring permeameter with Clive, his colleagues Robert Whittle, and my students. And I'd like to take this opportunity to acknowledge Clive Dalton's contributions in geotechnical engineering. The technology I'm going to present today mostly is distributed fiber optics technology, which enables continuous measurements or monitoring of strain, temperature, vibration, or noise along the length of fiber that can span many kilometers. I began working in this technology approximately 20 years ago because of Rab Fernie, a former chairperson of the British Geotechnical Association. He simply suggested I should explore this technology. And I did it and realized its potential for geotechnical engineering. That is, this technology can well suit it for our field because strain distribution in geotechnical structures varies spatially because due to the distributed load exerted by soil. The first field trial was conducted in collaboration with Cementation Skanska and Building Research Establishment. This technology can be categorized into distributed temperature sensing, DTS, distributed strain sensing, DSS, and distributed acoustic sensing, DAS. The fundamental principle is the transmission of light through an optical fiber. As the light travels, a small portion of light is backscattered at every point along the fiber. Since the speed of light is constant, at least where we live, the exact location of each backscatter signal can be determined through precise time measurements. Then by analyzing the frequency component of the backscatter light coming back from a given location of the interest, we can extract information about the strain, temperature, acoustic vibration, or sound at that point. And this can be done for every point along the fiber. While I cannot go into the technical details today, the key point is that this technology allows us to measure these physical variables continuously over long distances. Let's consider an example of a pile. As a load is applied at the top of the pile, strain develops within the pile. The largest strain occurs at the top and gradually decreases with depth due to shaft friction. As applied load increases, this triangular distribution shifts to the right. Eventually, a portion of the load transfers to the base of the pile, which can be observed through the strain measurements at the bottom. Now, let's look at the data over here. The left figure over here in the middle shows the load application over time, and the right figure presents depth in a vertical axis, and then strain, compression positive in horizontal axis. From this video, you can observe, and we can observe the triangular distributed strain distribution evolves as the load increases. The gradient of the strain, which is shown over here, indicates increasing mobilization of shaft friction. Additionally, at later stage of loading, we notice localized strain developing at a specific depth. This behavior is fluidly influenced by the construction details of the pile. By analyzing strain development over time, we gain insight into how the pile is actually behaving. The objective today is to explore the process of monitoring, learning, anticipating, and adapting in geotechnical engineering. I'll introduce new emerging sensing technology and data analytics technologies. I'll present 3 cases on tunnel, pipelines, and piles. And these case studies will examine how soil profile and construction process influence the performance of geotechnical structures. I'll also discuss how I assess actual performance versus assumed performance to derive the underlying mechanism that govern the behavior. By acknowledging the uncertainty, improving our ability to anticipate the performance, we can enhance decision-making in geotechnical engineering. One key discussion point will be utilization of concept of cautious and most probable, which some of my geotechnical engineering colleagues have been recently introduced within the framework of the observational method originally proposed by Professor Ralph Peck. Oops. Oh. In this ranking lecture, Professor Peck introduced the observational method. I'd like to discuss the 8 key components of this method, particularly focusing on the concept of most probable and most unfavorable states. Let's consider an example of an undrained shear strength data from a site shown in this particular figure. This site consists of 2 distinct soil layers. Each depth, we can determine an average or sort of a most probable, which is represented by the green line, as an average shear strength. Also, we can define a cautious estimate, which may be represented by the yellow line. And we often use this in our design. In some cases, the most unfavorable condition can be evaluated, which is shown in red. In his approach, Professor Peck said, perform sufficient site investigation. Assessed most probable and most unfavorable conditions, which is green and red. Establish design based on most probable, the average one, on anticipated behavior, which I'll call it design A. Select monitoring parameters and calculate anticipated values of these monitoring locations. Calculate values of the most unfavorable conditions. And then using that design A, select design modification option B, plan B. And then you go to the field, monitor, and evaluate actual conditions. Modify the design, use design B, if the movement is greater than what you expected. This is Peck's observational method, which is using most probable and most unfavorable. Our engineering parameters, such as strength and stiffness, often exhibit statistical variability. While the distribution shown here looks like a normal distribution, but it doesn't necessarily have to be. But most probable is probably located in the 15th percentile. In contrast, the cautious value, which is commonly used in geotechnical design, is often set at approximate 1 standard deviation below the average. Most unfavorable scenario, engineers may consider 1 in 1,000 probability, or putting a factor of safety to the cautious parameters. In comparison, structural engineers who often dealt with brittle materials may adopt 1 in 20 value as a conservative estimate. Just to remind you that Professor Peck was using this as a temporary structures. In monitoring, we typically establish target values, categorize them to different zones using color-coded system. Green, amber, red to define thresholds. In the US, we actually use yellow in traffic signals, but I'm in the UK now, so I'd like to use amber. In geotechnical engineering, uncertainty extends beyond engineering properties. We must also account for uncertainty in action loads. There are always uncertainty in selection and application of the mechanism or models, and construction-related activities. Collectively, these factors influence the anticipated performance in terms of movement in this particular case. To address these uncertainties in design, we adopt cautious values, which are highlighted in red, for all these uncertainties to predict the performance. We then conduct monitoring and compare the collected data against these predictions to ensure safety. The cautiously designed object with cautiously engineering parameters will give the red prediction. However, we can reanalyze the same design using most probable parameters to find our 50-50 green position. And you can start comparing that with your monitoring. Are you below green? Are you between green and red? Or are you in red? And that can be potentially give you the green, amber, red position as is shown on the below over here. Today's talk will demonstrate how our emerging distributed sensing and data analytics technologies can contribute to this framework by seeking to understand the actual behavior. So let's start with my tunneling case. In this section, I will discuss the uncertainty related to ground condition and action forces. The first project I'd like to introduce is based at CERN, the European Organization for Nuclear Research. CERN is the world's largest laboratory for particle physics. It has an extensive network of tunnels of more than 80 kilometers. There are two main accelerator rings. The largest is the LHC, which has a circumference of 27 kilometers. And then there's an older and smaller accelerator, the SPS, with a circumference of 7 kilometers. The SPS was constructed in 1974, which is about 50 years ago. Today, I'll focus on the TT10, which was built around that time, which is shown at the star location of this slide. The TT10 tunnel connects the proton synchrotron, which is shown over here, to the SPS as shown over here. Constructed in 1972, it features an incline tunnel with horseshoe-shaped design. The tunnel consists of primary lining, secondary lining with a waterproof membrane positioned between them. Also, there's a drainage system integrated along the side to collect groundwater. Seepage waters gather at the bottom of the tunnel and pumped out. This means that the tunnel is designed to be drained. The beam line, which is shown over here, must be precisely aligned, and physicists carefully adjust its height at specific locations. However, as shown in these photographs, structural issues have been observed. Cracks have formed, there's a heave on the floor, and some compression cracks at the crown and tension cracks at the shoulders. These deformations have made the impact adjustment of the beamline really difficult for physicists. The geology consists of this particular have two primary layers. The upper layer is moraine, which is a permeable deposit, while the lower layer is molasse, which comprise altering layers of sandstone and marls with varying thicknesses. The tunnel is situated within this molasse formation. As also illustrated in this figure, the molasse itself is further subdivided into layers of sandstone marl, which with unique characteristics that influence the tunnel behavior. Due to the tunnel inclination, the ground behind the tunnel varies at different locations. A series of two-dimensional finite element analysis were conducted for this project to assess the impact of soil layering on tunnel performance. Several finite element models developed by Vanessa Di Muro, who was a PhD student at that time, are presented here. This diagram shows the geological cross-section along the tunnel axis. So the geology changes go along as you go along the tunnel. The weakest geological layer encountered is called lumpy marl or very weak marl, which is likely to swell. The photograph on the right displays the core of samples of lumpy, very weak marl, illustrating its progressive degradation over time. The primary cause of this tunnel deformation is the duration of the drainage pipes due to calcite deposits, as shown here. They have progressively clogged the drainage system. As a result, water pressure behind the tunnel increased, leading to reduction in effective stress. This in turn has induced a ground swelling and an increase in the horizontal stress relative to vertical. And this is the assumed mechanism based on observations. To confirm the deformation mechanism, distributed fiber optic sensor was installed at two sections along the tunnel, CERN-1 and CERN-2. The sensor cables are attached to this in the circumferential directions, as shown over here, at various locations in CERN-1 and CERN-2. These cables were routed to the surface through a shaft, enabling remote measurements, as the direct access to the tunnel was not possible during the particle physics experiments. Given that the tunnel is in a radioactive environment, the radiant resistant properties of the fiber optic cables provided additional advantage. These plots represent strain data recorded at CERN-1 sections. The sensor cables were attached along the circumferential direction as shown in the red line in the diagram. There are 8 figures coming from different loops. The vertical axis is the actual strain, and then you can see from the spring line throughout the crown and to the other side of the spring line. The results consistently show compressive strain at the crown and tensile strains at the spring-like shoulders, indicating elongation deformation of the tunnel, as is shown over here. We all know that tunnel construction alters the drainage condition. Initially, immediately after the tunnel construction in clay soil, the pore pressure may change by shear-induced excess pore pressure and a little bit unloading in the undrained conditions. However, in this case, the drainage begins as the tunnel boundary remains the atmospheric pressure, effectively acting as a drain. This process increased the effective stress around the tunnel, leading to ground consolidation. Over time, clogging occurs, water pressure behind the tunnel rises, reducing the effective stress, causing the surrounding soil to swell. This slide shows the tunnel deformation mechanism at different stages as described in the previous slide. According to Professor Mayer's Rankine lecture and our subsequent research, the tunnel often undergoes squatting deformation during the consolidation stage. While the consolidation of the surrounding ground of the soil can take many, many years, tunnel deformation occurs shortly after excavation as the soil near the tunnel is close to the drainage boundary. However, as clogging starts, an opposite trend is observed and the tunnel elongates. The CERN-2 section exhibits significant variation in tunnel deformation. At higher elevation, which is shown number 1, the tunnel was surrounded by uniform marl and elongation was minimal. As you go a little bit deeper, at lower section, the geology changed with a medium weak marl on the top and marl in the bottom. Here, strain values were about 100 to 200 microstrains. However, when the tunnel passes through the section of medium weak marl on the top and very weak marl in the middle, the strain recordings were significantly higher. Once the tunnel transitioned back into the marl, the strain level decreased again. This slide shows a finite element model of two finite element simulations. First case models, the tunnel in a homogeneous malformation. The second case models the tunnel in a layered geological settings with a medium weak mal on the top and very weak mal at the bottom. The drainage conditions at the tunnel boundary were analyzed through a series of stage simulations. In the first stage, seepage follow tunnel construction was modeled, as shown in the figure on the left. The second simulated a present-day scenario which water pressure at the tunnel boundary gradually increased up to the top of the molasse formation. Finally, third stage projected a potential future scenario where water pressure continued to rise, reaching to the surface. Two different soil models were used for simulation. The first was conventional Moore-Coulomb model, while the second was more advanced nonlinear anisotropic-based critical state soil mechanics that we used to use in London clay. And both models exhibit similar trends in deformation behavior. However, in the homogeneous case, there was radially outward deformation, uniform deformation with small unloading, which resulted in negligible bending. However, in the layered case, the tunnel underwent vertical elongation with an increase in the diameter in the vertical direction and decrease in the horizontal direction. This deformation pattern led to bending strain along the spring line, which is shown over here, and then the actual compression at the crown, as illustrated in the bottom figure. These two figures on the left illustrate the water pressure distribution in the layer case. Due to varying permeability values assigned to different layers, resulting water pressure pattern deviates from the typical radial circular profile we observe in a homogeneous case. The key finding of this work is soil layering influenced the deformation pattern of the tunnel due to not the layering and the stiffness, but also the water pressure around the tunnel. And this led to a mechanism show that the layering affects the elongation. The tunnel displacement results from the finite element model were compared to the cross-sectional survey measurements collected since 2013. The measurement data represented by solid dots show a similar trend of the FE simulation result as the water pressure around the tunnel was increased to 160 kPa. To assess the future potential deformation, the simulation was extended to model the water pressure that rises to 350 kPa. The predicted results shown in the red lines indicate the horizontal displacement could reach up to 2.5 millimeter under these conditions. So while I present this case, these may be very obvious to you, but it was not very obvious to us at the beginning. And we decided to realize the significance of the soil layering and tunnel behavior with water pressure changing was a gradual process for us to understand what's going on. Monitoring provided initial insights into deformation mechanism. However, we were very puzzled with the magnitude or variation of that effects changed. This led to a deeper understanding of the impact of soil layering using finite element simulations. And this study showed that the importance of accurately capturing ground conditions during construction to ensure long-term stability of our infrastructure. CERN has implemented several engineering tasks, including not using horseshoe-shaped tunnel anymore for future tunnels, and prioritizing continuous monitoring of structural movements. For example, CERN is using laser scanning and photogrammetry to assess the changing in their assets. Very nice, isn't it? In collaboration with the University of Cork, they're using AI-based crack detection technologies. They're adopting robots to automate inspections. Actually, the one on the bottom right, yellow dog, is one we have at UC Berkeley. It looks fun, isn't it? At UC Berkeley, our research focused on leveraging massive data from tunneling machine and applying machine learning techniques to enhance analysis and prediction capabilities, including capturing ground conditions. This case study, which uses the tunneling data collected in Seattle, involved a 17.5-meter earth pressure balance machine, which records 6,000 features or data sets every few seconds. The data was then aggregated every 20 millimeters or per tunnel ring. The data, example of the data set is shown on the figure on the right, and we have 6,000 of these data sets. Perhaps we can think of tunneling machine like a giant CPT. Both penetrate ground and both produce signals. But CPT produces 2 or 3-dimensional data, whereas TBM produces high-dimensional data sets. CPT has a constant penetration mechanism, whereas TBM has a complex penetration mechanism. The complex interactions among features are recorded in these high-dimensional data sets. In this animation, the borehole data serve as a ground truth as the tunnel advances. A data-driven geological model is developed by sequentially leaking borehole data with tunnel machine data as it advances. Blue represent clay soils, while orange indicates sandy soils. It appears that the geological interpretation made by the expert, as shown above, is similar or closely aligned the machine learning model-driven interpretation as shown below. So the blue is the clay one, and the sand is orange one. When a particular section is examined closer, a small pockets of silt and fine sand represented by green, as well as till deposit, represented in purple, can also be observed in this section. The machine learning model appears to capture these localized features along with the overall transition from clay to sandy soils. So this enables the potential for automatic real-time identification of the ground conditions during construction that can be used for future proofing. This slide presents a case study of twin tunnels in Osaka, Japan. The tunneling process was carried out one direction first, going this way, turn around, and to excavate the parallel tunnel, the second tunnel. The geological interpreted profile from the borehole along the tunnel alignment is illustrated in this figure, where clay is represented in blue, orange is gravel, and then sand is in yellow. Machine learning models were developed to interpret geological conditions based on tunneling data. In case one, a model was trained using the data from the first tunneling drive and then applied to predict the geology from the tunneling data of the return drive, but the model was not updated sequentially. So we only use the data model from the first drive. In case two, the data from the first drive was not used. The sequential modeling approach was used for the return drive only, similar to the one I just showed you from the Seattle case and the first drive that we used in case one. In case three, the model was initially trained on the first tunnel drive, but the model was sequentially improved during the return drive. And the geological interpretation produced by these three models are shown on the right. Of course, we don't know what's happening between the boreholes, but the only thing you can do is to compare with the borehole data. And when compared to the borehole data, obviously case 3 is better than the obvious case 1 and 2. In other words, machine learning model has to keep on learning as well as we do. This slide illustrates the interaction between various parameters in the Seattle case. Blue represent positive correlation, meaning that one parameter goes up, the other parameter goes up. The red represents negative correlation. One parameter goes up, the other parameter goes down. So you have some correlations. And the white, which means if you don't see anything, that means that there's no correlation. I'm not sure what you can get out of this particular slide. It's a nice slide. But due to the complexity of these interactions, direct interpretation is not very straightforward. However, we can utilize advanced tools such as Bayesian networks and structural learning algorithms to analyze machine learning outputs. In this study, two sets of the data, one from clay soils, and then other from the sandy soil dominant, and the interaction diagram for each soil type was created. The results indicate strong conditional dependency between advanced speed and chamber pressure when the machine is operating in clay soils. This suggests an increasing chamber pressure is closely linked to the tunneling speed advancement that it's making. In sandy soil, a strong conditional dependency was observed between screw conveyor operation, or screw conveyor rotation speed, which is often controlled by the operator, and the chamber pressure. So these two cases highlight different operational dependency in varying ground conditions. And these findings provide invaluable insights, but more work needs to be done. And for me, this is an exciting area for us to go further. Are you still okay? I'm going to part two. Buried infrastructure. This section discusses about the buried infrastructure pipelines. Many water pipelines in London, I assume, I think I remember that, in the Bay Area where I live, are old, leading to an increasing number of water main failures. This map illustrates ground movement-related water main breaks that have occurred in the East Bay Area where I live over the past 30 years. Due to the region's hilly terrain, landslides are common, particularly areas affected by the Hayward Fault, which is shown in the dotted lines. The yellow star marks the location of my campus, UC Berkeley campus, and Hayward Fault runs directly through the campus. And now you know why I moved to Berkeley. Oops. The East Bay water supply is managed by East Bay Municipal Utility District. I call it East Bay MUD, the second largest water utility in California. Some of the oldest pipelines date back to 1880s, similar to what we have here, as shown in this particular graph. And probably here is much older. Over the past century, various materials have been used for pipeline construction, beginning with cast iron, moving to asbestos cement and to steel, and more recently, non-metallic plastic pipes. This evolution in material selection highlights the difficulty of adhering a 100-year design life as our understanding of optimal materials continues to change. East Bay MUD maintains approximately 6,700 kilometers of pipeline and experiences over 1,000 breaks annually by ground movements and also corrosion. Currently, a utility replaces about 40 kilometers of pipeline each year, meaning that full system replacement will take between 150 to 200 years, which is more than the design life, as you know. This raises a critical question or challenge: how can we develop more effective strategies for renewing our aging infrastructure? This satellite map highlights the East Bay area. The yellow star marks the location of our campus, while the blue star indicates the site of our case study, which is near our campus. Our campus, which is shown in this particular pink zone, received water supply from this particular treatment plant located on the opposite side of the hill at the elevation of 107 meters. Since our campus sits on the elevation of 109 meters, additional water pressure is required for distribution. To achieve this, water is pumped daily to the two reservoirs shown on this map, which are situated at an elevation of 150 meters. Unfortunately, this pipeline supplying this water must cross the Hayward Fault, as shown on this figure. So in collaboration with East Bay Mud, we had the opportunity to install fiber optic cables on two new constructed HDPE plastic pipelines. The Hayward Fault is a right lateral strike-slip fault where the left side moves northward and the right side moves southwards. Two pipelines have a diameters of 0.9 meters and 0.55 meters. 3 fiber optic cables were attached along the axial direction, each pipe, one at the crown and the two at the 45 angle from the horizontal. It was not possible to put on this lateral part 90 degrees because it was difficult to put your hand in it. The pipelines were buried at a depth of approximately 1 meter. Also, temperature and strain sensing cables were embedded within the trench, and the cables are shown over here at the bottom. This video presents on one of the instrumented pipelines installed within the trench. 3 distinctive lines runs along the pipeline, indicate the placement of fiber optics. These cables were placed beneath the tapes using epoxy adhesive to ensure firm adherence. Please note that there's a gap, small gap between the trench and the pipeline. The gap is rather small. The trench was filled with sand near the pipe, but not compacted well, and gravel was placed above near the surface with good compaction. These plots show the progression of strain over time in the two pipelines. The horizontal axis presents the pipeline distance from one end to the other, so 200 meters and then about 150 meters. While the contour indicates strain magnitude, and the red shows tensile strain. Change in over time is shown from the top to the bottom in the vertical direction during the 18-month period of readings. Both plots shows tensile strain observed, developing around the fault location, with a magnitude ranging about 100 to 200 microstrain. This video illustrates the evolution of strain over an 18-month monitoring period. The data reveal a pattern of tensile strain are concentrated in the middle section of the pipeline where the fault is. And then we can start to create a mechanism of tensile deformation happening in the middle and small bending on the two sides. When recording is done, it is essential to assess its precision, as demonstrated in this figure. Accurate measurement ensures reliability and enhances the validity of the analysis. In this study, multiple readings were taken to assess the precision of attached sensors. In this particular case, it's about 10 microstrain. And you can do that for every point along the fiber. Distributed strain data, which is a strain, can be integrated along the axial direction to get the relative displacement profile from one end of the pipe to the other pipe in terms of stretching of the pipe. And this video illustrates how the displacement profile evolves over time. Seasonal variation are evident, with slight compression occurring in the winter and minor extension in the summer due to the thermal contraction and expansion of the plastic pipe. However, such thermal-induced axial movement is constrained by soil resistance in the axial direction. On the other hand, the axial extension around the sort of area of the fault zone is about 4 millimeter. And this is due to that localized strain accumulation over the region that I showed you earlier. That as the distributed strain are integrated, errors accumulate as you integrate over distance. A theoretical formula can be derived to quantify this accumulation as shown in this equation. The error originates from the precision error which I showed you earlier, as well as the measurement spacing, as denoted by h equal 0.1 meter in this case, and the integration distance. The estimation indicates the error at the 260 meter endpoint, which is the endpoint over here, is approximately 0.1 millimeter, which is relatively small compared to the 4 millimeter that we measure. The 4 millimeter elongation observed around the fault line over the 18 months can be compared with the data from the inframetric synthetic aperture radar, INSAR, which have been collected over more than 10 years. Although INSAR data exhibits significant scatter, it statistically shows that relative movement between the Pacific plate, which is shown in red, and the Northern American plate, shown in blue, with a displacement rate of approximately 4 millimeter per year. So this aligns well with the estimated derived from the distributed fiber optic sensor measurements. We have two fiber optic cables on the two sides, and opposite of the pipeline. These data sets allow us to derive the bending strain, which can then derive integrated twice to estimate the lateral displacement of the pipeline, assuming pin boundary condition at both ends. And this video represents the results. Actually, it shows a surprisingly lateral movement of approximately 100 millimeter, about 10 centimeters movement. Area estimates indicate uncertainty of about 15 millimeter at the midpoint, which is smaller than what we measure, which is 10 centimeter or 100 mil. So at the beginning when I saw this, which was really difficult, hard to believe. However, it was observed that the temperature of the water inside the pipeline varies both daily and seasonally, as shown in the top left figure. Also, internal pressure fluctuates throughout the day as the water pumps to the reservoir and then released for distribution. Plastic pipe has a large thermal expansion coefficient. A simplified soil spring analysis, interaction analysis was conducted to examine the effect of temperature and internal pressure variation on the pipe movement. When the lateral soil spring was assigned to be minimal resistant, thermal expansion and contraction of the pipeline allowed lateral movement, similar to what was estimated from fiber optic sensor, as illustrated in this figure. Construction photographs showed earlier indicate that trench was narrow, and it is unlikely the proper soil compaction was not achieved around the pipe. However, the location of maximum lateral movement occurred depend on actual resistance of the soil. When there's no actual resistance, which is not likely, the maximum location is shown where the curvature is maximum. When there's some actual resistance, the maximum location shifted, as shown in this right figure. More work is needed to develop a predictive movement or predictive model, but the key takeaway is that daily and seasonal variation must be thoroughly understood before assessing the effects of fault movement on pipeline displacements. Monitoring with distributed fiber optic sensors enables evaluation of anticipated performance, not only for a few points, but continuously along the entire asset. So in this context, it is essential to know the variation in distributed strain profile predicted by different models to assess how well they align with the observed performance. Let's consider a transverse deformation mechanism. As illustrated in this particular figure, one soil blocks move relative to the other at an angle of beta. As the soil body shifts, pipeline experience a combination of axial tension as well as bending. An analytical solution can be derived by incorporating key factors such as soil pipeline interaction in the axial direction or in the transverse direction and the transverse section, the elastoplastic response of the pipeline material itself, and the effects of internal pressure and temperature. And Professor O'Rourke's Rankine lecture paper is a good place to start knowing about this. A very nice analytical solution for this problem was proposed by Dr. Karamitros in 2007, which is shown over here. Additionally, this problem can be approached using numerical methods, such as discrete model using soil spring analysis, or make it fully continuum with a soil continuum as a pipeline continuum as well. And I'll call it full continuum models. In the full continuum model, you can apply internal pressure to the pipe or without pipe internal pressure. And the full rupture happens, the pipeline behaves in a different way. When pipeline is not pressurized, it can experience ovalization as shown in the bottom figure. So the finite element models with full continuum can do this. But let's consider a scenario where we have an internal pressure applied, but they examine the difference in terms of distributed strain profile across analytical solution, discrete model, and full continuum model. Sorry, this is a little bit a busy figure. The figure on the left compares the distributed profile predicted by analytical model and the discrete soil spring model. This is the distance, fault is in the middle, and then longitudinal strain in the vertical axis. The top figure represents strain profile for small fault movements, 10 to 30 centimeters, while the bottom figure corresponds to larger fault movement, 50 to 150 centimeters. The strain profile predicted or given by the analytical solution are solid lines in color, and those from discrete model, the soil spring analysis, are dotted lines. And because of the assumptions made in the analytical model, there's some drops in the predicted strain profile, whereas the discrete model produces smoother results. Also, the overall shape of the strain profiles differs between two models. The figures on the right compare the distributed strain profile obtained from the discrete soil spring analysis model on dotted lines and full soil spring pipeline continuum model in a solid line. For small fault movement, the two models produce similar results. However, as the fault displacement increases, the strain profile begins to diverge. And this discrepancy arises primarily from the three-dimensional soil deformation going around the fault zone at large fault movements, which discrete model does not fully capture. The key point, these are just examples. The key point here is the choice of model also affects the anticipated performance when distributed strain profiles are considered for monitoring. Actually, in some cases, real-world conditions differ from our expectations. At that particular site that I showed you earlier, the new pipeline was installed adjacent to abandoned pipe, as shown in this photo. So it remains uncertain whether the abandoned pipe will provide protection during a large fault movement or contribute to potential damage. So it seems better to monitor this pipeline, which is a critical one, for this particular water distribution system. The key takeaway is that once a pipeline is buried, we're not going to see it for the next 100 years. Therefore, why not embed intelligence during construction for future generations? In this case study, the monitoring data provided valuable insights into deformation mechanism of the HDPE pipeline, plastic pipeline, particularly in response to daily and seasonal temperature variations inside the pipeline. Understanding these strain fluctuations during normal operation enables better understanding and better preparation for potential strain changes caused by large fault movements during an earthquake. The pipeline is designed to withstand large ground movement after a large earthquake, but the strain sensors will allow for assessment of its residual life, informing future renewal decisions. Distributed fiber optic sensors can be adopted for proactive maintenance, ensuring both economic efficiency and long-term safety. So what are the future opportunities? This slide details our current project with the California Energy Commission and electrical gas company PG&E, in which we leverage various distributed sensing technology, INSAR, LiDAR, UAV, distributed fiber optics wireless sensing system, to evaluate the performance of gas pipeline underground movements. The project aims to proactively incorporate distributed strain data sets to enhance predictive model performance rather than the point measurements over the lifespan of the pipeline assets. So fiber optics can be integrated into any structures. So imagine you can do whatever you like here within the pavement structure. In the illustration on the top figure, cables were installed within the asphalt, transforming the pavement into an interactive surface. This configuration enables the monitoring of movement or patterns on the pavement surface. For instance, a dog runs, and the movement is detected. And actually, the movement strain is about 0.02 microstrain, 20 nanostrain. Similarly, when a person runs or when you're happy, you hop, the system captures both hopping pattern and the corresponding strain gradients. Strain measurements, sorry. Fiber optics can be equipped with distributed acoustic sensing, can function as geophones. In this study, a seismic survey was conducted to assess the subsurface condition at a site, the same site that I showed you earlier, where fiber optics cables were embedded in the soil. The S-wave velocity maps obtained from distributed acoustic sensing, DAS, and conventional discrete geophones are presented in the slide for comparison. Fiber optics are already embedded beneath the pavements for internet communication, as illustrated in this particular figure. A company called FiberSense, where my former PhD student served as a vice president, is collaborating with Thames Water to detect water leaks across London using distributed acoustic sensing for noise detection. The map displayed here highlights potential leakage locations identified through acoustic signal captured by fiber optic cables in London, and maybe your house is close by. Some of these locations were excavated to verify and address the detected leaks as shown in the photos at the bottom of the slide. Here's a case study in which the existing telecommunication cable, fiber optic cable, were used to detect the peak ground accelerations during a small earthquake in San Francisco, which is shown in this particular line of the cables. The level of ground motion is linked to the geological variation at that particular site to understand how the ground is behaving when the earthquake happens. So this will be my final section. I hope you're still okay. So in this final presentation, I'll discuss deep foundations. This is a test pile case study at Newfoundland Canary Wharf in London. And first of all, I'd like to acknowledge my long-term collaborator, Duncan Nicholson, and many of his colleagues who played key roles in successful execution of this project, as well as many piles projects during my time at Cambridge. The test pile has a diameter of 1.5 meter and the length of 51 meters. It was equipped with O-cell or bidirectional loading device at the base. The pile was constructed in a soil profile comprising made ground, river terrace gravel, Lambeth group, consists of, as you know, sandy silty clay and silty clay layers, Thanet sand, and chalk. Fiber optic cables were attached to the reinforced cage. 4 strain gauges were attached to the reinforced cage at 2 sides, and the temperature cables were positioned at 90 degrees intervals. All cables were connected to a single line, and readings were recorded accordingly. The cables were installed with a minimal disruption to the construction process. The bottom reinforcement cage was first instrumented with the fiber optic cables. At each subsequent cage was lowered down into position. The cable in rotating drum were fed with the cage. The fiber optic cables were attached at several intervals by the construction crew. In conventional power loading tests, vibrating wire strain gauges are commonly used. Each require individual cable. When multiple strain gauges are installed, large number of cables extend to the top of pile, as illustrated in this photo. In contrast, this particular instrument pile with the fiber optics have a few fiber optic cables sticking out of the top. Thick cables are designed for temperature monitoring, while the thinner ones serve as a strain sensor. At the termination point, these cables are spliced together into a single line, which is then connected to an analyzer interrogator for data collection. For instance, in the Newfoundland case, a single fiber, one line, generates thousands of data along the 50-meter pile. Thermal integrity profile is increasingly being used to detect construction anomalies in piles. This method monitors temperature variation during the hydration and curing process of a concrete pile. This video illustrates how temperature profiles recorded by the 4 cables change over time. The temperature, went further too fast, but the temperature rise occurs more rapidly at the bottom as the concrete was poured earlier, and the blue and green line profiles correspond to one side of the pile, while the red and yellow profiles represent the opposite side. The middle figure represents the temperature profiles at 3 different times, 4 hours, 14 hours, and 34 hours. So at the given depth, there are 4 temperature readings recorded at 4 different locations near the concrete, near the sort of concrete soil interface, which is shown over here. Example of 2 depths are shown in the figure on the right, where you see 4 data sets at a given depth. You can see a temperature change, increase and decrease. There are 1,000 temperature data sets along the 50 meters measurement section for each cable, hence we have 4,000 data sets. In this study, one-dimensional finite element analysis of radial heat transfer were performed for each data set. The FE model shown here consists of central nodes representing concrete, outer nodes representing soil, with additional node positioned at where the fiber optic cable is located. Initially, all time varying temperature data was average. Heat source and the soil properties, thermal properties, were then calibrated to ensure the average FE model accurately represents the targeted pile radius. After calibration, the pile radius of each monitoring point was determined by adjusting the position of the node that represent the concrete and soil interface, ensuring that the computed measurements are similar to the temperature data. The analysis was conducted in 4,000 data sets. Then the estimated pile shape is illustrated on the right side. The results indicate a smaller diameter within the Lambeth group, with a larger diameter as observed in the Thanet group, Thanet sand. First of all, I'd like to point out the image shown here is exaggerated in horizontal direction. To get more accurate representation of its actual shape, it would be best to review it at its actual true scale. This pile shows the pile at the true scale, where the surface variation is smooth, with the radius varying between 10 to 40 millimeter with a 750 milli diameter pile. Radius pile. In my view, this is a well-constructed pile. As we move, and then you can see the shape of the pile in true scale. Not the real scale, but one dimensions, right? As we move to the following slide, I'd like to remind you that the horizontal axis is exaggerated to highlight the variation. However, in reality, the spatial variation is gradual. Bidirectional loading test was performed on this pile with a load applied at the base. The expected strain profile follows a triangular shape where the gradient of the strain corresponds to mobilized shaft friction. This figure represents the strain profile measurements at different loading stages from the orange moving to purple. As applied load increases, the size of the triangular strain profile expands and its gradient steepens. This indicates that the shaft friction is progressively mobilized with the increasing load. Vibrating wire strain gauges were installed in this pile, and the recorded values are given for a given load are plotted against the distributed strain data shown over here. Correlation between the two data sets seems reasonable. However, the variation in strain or the waviness observed in data, this distributed fiber optic data, is somewhat disturbing. And many of my colleagues didn't like it. Again, the waviness is exaggerated due to its scale, but the strain variation is gradual spatially, like the one I show you in the thermal profile image. And there are many points to make this waviness. The previously shown data represent the average strain of the 4 cables that we had. When the data of each strain cable is plotted separately, it is interesting to observe that all exhibit similar waviness pattern, despite being entirely independent parameter measurements. The spatial data interval is about 10 centimeters, meaning that waviness is not the result of an individual data point fluctuating up and down. It's a rather smooth transition across multiple readings. And I'll revisit this issue later on in the presentation. The distributed strain profile can be integrated to obtain displacement profile by differential integration at different loading stage, as shown in this particular figure. So we're loading from the bottom, so the displacement is larger at the bottom and decreases as you go to the top. And the displacement measure displacements or integrated measure displacements are on the order of 3 millimeters. For validation, several extensometers, there were 6 of them, installed in this test, allowing a comparison between the data, that particular extensometer data, and the fiber optics data derived displacement. In these figures, the vertical axis represents displacement, while the horizontal axis replaces applied load. The red is in the fiber optics, and the black are the extensometer readings. They closely align each other, demonstrate the consistency between the two measurement methods. It's too good, but it is true. As shown in the previous slide, the displacement profile can be derived from the different fiber optic strain data. Furthermore, by assuming a stiffness of pile, the force distribution along the pile can be computed, and the gradient of the force profile is directly proportional to the mobilized friction. So comparing the displacement and shaft friction provides valuable insights into the shaft mobilization mechanism at different soil layers and different displacement and different loads. The TZ soil spring analysis is commonly used to evaluate the load displacement characterization of pile. Using the procedure I outlined earlier, the TZ relationship for different soil layers can be estimated, as illustrated in these figures. In these graphs, vertical axis is the shaft friction in kPa. The horizontal axis represents the relative displacement between the greenfield soil and the pile. The TZ curve for the Thanet sand exhibit well-defined mobilization of shaft resistance with increasing displacement. In contrast, the TZ relationship for the Lambeth group shows an initial slip-like behavior at the beginning of displacement, followed by a rapid increase in shaft mobilization. It is possible that the minor necking or minor contribution over here derived from the thermal analysis contribute to this TZ relationship in the Lambeth group. Larger diameter in the Thanet sand may have played a role in more effective mobilization of shaft resistance. The key takeaway is that if fiber optics can be embedded during construction, it is possible to use the data for construction quality control, real loading, future-proofing against earthquakes or nearby construction, and reuse. As a complementary analysis, I would like to present apparent radius profile derived from the thermal analysis along with a strain profile obtained from the loading test. Again, there are two independent data sets, one from the temperature cable, which is shown on the left, and one from the strain cable. It appears that there's some correlation between the two. When the apparent pile radius is larger, the strain is lower, represented by red dots. When the apparent radius is smaller, the strain is higher, represented by blue dots. It has been discussed that the waviness observed in the apparent radius profile may be attributed to the TREMI placement process. The plot in the middle illustrates the location of TREMI splits and lift divisions, which is shown in this step functions. It appears that the certain lift, which is shown in the sort of red over here, the apparent radius is larger in the middle and smaller at the lift boundaries, suggesting a potential influence of the concrete placement sequence on the pile geometry. So maybe the TREMI operation may have contributed to observed small waviness, but it's a very small variation. Further on, we optimize the parameters of that TZ-based pile analysis by first adjusting the Young modulus of the concrete to match the overall trend of the strain profile. Then we fine-tune the radius, the up and downs, and TZ parameters to align with the waviness profile. And this video illustrates the optimization process. The figure on the left illustrates the optimized, it's not true, but this is optimized variation in Young modulus. To obtain realistic constraints, we limited the optimization so that the Young modulus did not vary by more than 10%. Lower values were derived in Lambeth group section compared to Thanet section. The middle graph, graph in red, shows the radius profile obtained from the strain data with the optimization, while the thermally derived apparent radius profiles from that thermal measurement are represented by other colors. It is important to note that both sets of the data are calibrated once, so that's not represent the actual radius, but it shows the variation potential in the radius. However, when we calculate the gradients, to compare the two, when we calculate the gradients of these values and plot them together, we obtain the figure on the right. This comparison shows the gradient profile align relatively well, suggesting the waviness observed in the strain profile correspond to waviness derived from the thermal integrated test data. So this, for me, this is really interesting. I'm not sure whether it's for you, but that's what I wanted to show. In this case, monitoring enabled the estimation of pile radius profile and the assessment of pile performance at the various locations during loading. Key takeaway was the relationship between shaft mobilization, soil properties or soil around it, pile diameter, and construction effects, which enhanced our understanding of soil pipeline interaction. If the distributed fiber optic sensing technology can be adopted, monitoring data could be used for quality control, operational load assessment, and potential future reuse of foundations. This in turn would contribute to more reliable and cost-effective construction practices. I'd like to conclude my talk using the following 6 slides, so 6 boards, sorry. If we monitor the performance of our geotechnical infrastructure using what we call 50-50 prediction approach, we can begin to understand what our 50-50 threshold is for various uncertainties that we need to be considered. So rather than just going for red, let's try to find our 50-50. In pile test, we typically measure load settlement at the top, and we may have green, amber, and yellow at different steps. However, with distributed sensors, we can design deeper insight to how soil layer adjacent to a pile contributes to the soil overall resistance. Comparing displacement and shaft friction provides valuable insights to the shaft mobilization mechanism at different loads, different pile displacement, and different soil layers. Although I have not shown any retaining wall case today, a similar approach can be applied here. As shown, as you excavate, you can have a green, amber, and red. During the design stage, we can conduct 2 designs with and without the last prop support and define green, amber, red for each design at every excavation stage. The model parameters of the 2 stages designs can be updated during the construction stage. If appropriate, and if you're confident with your 50-50, the design without the last prop may be selected, which saves both construction time and cost. So we may not be able to, we don't have to use the red one to go further and go to a deeper excavation. If the monitoring data is in the red zone, we need to make immediate action because it's beyond what you've thought as a cautious parameters. If the monitoring is within the amber zone, which is shown in the middle, we need to, the actual ground is a bit worse than the average. The data needs to be reviewed, and we need to keep everyone informed about the progress. If the monitoring data consistently show that they are in the green zone, it is possible that it is over-designed. Over-design can come from selection of engineering parameters, and many Rankine lecturers who are here today have explored the degradation of stiffness from small strain to large strain. And by conducting back analysis of case study using distributed strain data with addition, we can refine our approach to select appropriate stiffness or strength values, leading to more efficient and informed design choices. We also recognize the complexity of soil behavior. Laboratory measurements are conducted along specific stress paths, often using perhaps distributed soil samples, whereas in the field, soil behavior is influenced by the combination of different shear modes and construction effects. And over the years, here in London, by experience, we have accumulated valuable knowledge to refine our design approaches. For instance, in undrained elastic analysis for ground movements evaluated in London clay, the values of undrained Young modulus have been updated to support more economical design. In the 70s, we have these values, but now stiffness values account not only for loading direction, reflecting the anisotropy of the clay, but also system stiffness. However, it's taking 50 years. We need to do faster and more economically. So I want to emphasize that these ideas are not really mine. They come from a series of studies discussing about the next generation of the observational method, which have been proposed and developed by many researchers over the past decade. And I would like to acknowledge them for their contributions. There are several guidance documents available for applying the new generation of the observational method, enabling more economic and efficient design. Understand that recent Eurocode has incorporated the concept of most probable value, further reinforcing this approach. Also, there are ongoing initiatives in developing a robust geotechnical database And also we have advances in data analytical tools, which enhances our ability to assess, improve geotechnical infrastructure performance. So in summary, the engineering assessment can start with predictive performance, using both most probable and cautious parameters. Monitoring then conducted to evaluate where the collected data falls within the various categories of green, amber, or red. When multiple readings are obtained during construction or nearby sites, decision parameters can be refined through back analysis, which represent the learning stage. We can continue this cycle until we're confident about 50-50. Then we can adopt to a new norm. So let's try to find out more about our 50-50. In summary, my talk today aimed at highlighting innovation in sensors and data analytics. They're providing exciting opportunities to understand the actual performance of infrastructure during construction and operation. For instance, embedded distributed fiber optic sensors can provide valuable strain data that no other sensor can offer. A monitoring system should be integral to the construction package. This ensures long-term proactive operational monitoring, contributing to quality control, maintenance, resilience against hazards, and reuse. The new generation of observational method is a proactive integration of design calculations and monitoring. This means use of cautious parameters and most probable parameters, and understanding of how they behave. This in turn allows us to acquire knowledge from the monitoring data and appreciate different mechanisms and uncertainties. The overall goals are to enhance economic efficiency and to ensure future sustainability. So we can start by testing our 50-50 using our sensor technology and data analytics. The work presented today is a result of contribution from the colleagues I have had a privilege to work in the past and continue to collaborate with today from the University of Cambridge Center for Smart Infrastructure and Construction, and from UC Berkeley, Berkeley Center for Smart Infrastructure. Field works require a lot of collaborations, and many findings today are from their hard work. While there are many to name individually, I want to express my sincere gratitude to all of them for their brilliant insights and support. Thank you very much for listening. Thank you, Andrew.
I now call upon Professor Lord Robert Mayer of the University of Cambridge to give the vote of thanks on behalf of the British Geotechnical Association.
Well, ladies and gentlemen, it gives me great pleasure to propose the vote of thanks to Professor Soga for his exhilarating Rankine lecture. In his introduction, Malcolm Bolton described Kenichi as a T-shaped powerhouse, strong roots in a recognized discipline, but branching out to connect with other disciplines. This evening, Kenichi has amply demonstrated these outstanding qualities. He has shown us how distributed sensing and data analytics can be applied in truly innovative ways to improve performance-based design, to improve construction, and improve maintenance. Kenichi introduced his lecture by drawing our attention to many emerging sensor technologies, computer vision, automated inspections with photogrammetry and robotic solutions, LiDAR, INSAR, and the use of drones and satellites, wireless sensors, and distributed fiber optics. He rightly emphasized that by knowing the actual performance of our infrastructure, we can improve design and construction processes, and we can react quickly if an unexpected event develops, all of central importance to geotechnical engineers. He neatly connects much of the material in his lecture to the philosophy of the seminal 9th Rankine lecture given by Ralph Peck on the observational method in 1969. A central theme of Kenichi's lecture has been distributed fiber optic sensing, a technique that he has pioneered for many infrastructure measurement applications. Much of this work was done when he was at Cambridge. It was a privilege to have collaborated with him on smart infrastructure. He was always a pleasure to work with. His enthusiasm was always immense, as you will have seen this evening. His lecture has shown us how distributed fiber optic sensing can provide unique strain data that no other sensors can give. He has demonstrated how fiber optic sensing and other innovative techniques have been successfully applied to a wide variety of infrastructure. His examples range from tunnels in CERN, Seattle, and Osaka, buried pipelines crossing faults in California and subjected to earthquakes, to deep foundations in London and California. The essence of all his material is the creation of intelligent infrastructure. He challenges us with the notion of routinely embedding intelligence in all construction. He is, of course, absolutely right, but try telling that to most procurement departments. We still have a long way to go. We need more compelling advocates like Kenichi. As we've come to expect from him, he's combined basic science with new developments in technology. He has presented superb examples of combining innovative measurement techniques and observations with insightful analysis, the armory of the very best geotechnical engineering. He's been an excellent advocate of monitoring systems being an integral part of the whole construction package, providing quality control during construction, maintenance strategies throughout operational life, resilience against sudden hazards, and eventual reuse. He also importantly illustrates the immense value of proactive integration of design calculation and monitoring, leading to reductions in conservatism, the enemy of civil engineering, more economic design, and improved future sustainability. So, ladies and gentlemen, we've been very fortunate this evening to have been at a lecture by a visionary powerhouse, Professor Kenichi Soga. With great clarity and fascinating examples, he's shown the geotechnical profession the future direction we should be moving in. His lecture is a stirring call to arms for us all to geo-adapt. On behalf of the British Geotechnical Association, I thank you, Kenichi, for delivering this outstanding 67th Rankine lecture.
Thank you very much. Oh, that was really nice.
It was really superb.
Thank you very much.
Well, as you know, this lecture is followed by the Rankine dinner. For those of you who've purchased tickets, the dinner is preceded by a reception in the senior common room, which is on this level, and it's, as you go out of the door, it's directly opposite you. Could I have the closing slides, please? There we go. For those of you, oh, that's it, there we go. For those of you who can't make it to the dinner, the early career group of the BGA will be hosting an informal networking at Imperial College's East Side Bar following the lecture. The bar is located next to Prince's Gardens, and there should be signs in place to allow you to get there. All lecture attendees are very welcome, and there will be a mix of non-alcoholic and alcoholic drinks available. Although, do note, it's a first come, first served. The next event is the winner of the BGA Case Histories Award, and I've just noticed it doesn't say the date on there, apologies for that. It's on the 29th of April at the Institution of Civil Engineers. Following that, we have the BGA Annual Conference and AGM on the 25th of June, again at the Institution of Civil Engineers. And following that, we have the Earthworks 2025 conference, which is in September. This is the fourth biennial conference of the British Geotechnical Association. Will be held at the University of Birmingham between the 16th and 17th of September. There are still opportunities if anybody wants to sponsor that, or if you want to put an exhibition stand up. And a reminder that student membership is still free. So if there are students in the room and you're not a member of the BGA, please look at the website and join. The name of the 2026 Rankine lecturer will be announced at the dinner. For those not attending, the name will be posted on the BGA website at around 11:30 this evening. Finally, it just remains for me to wish you an enjoyable evening, have a safe journey home, and thank you for attending. Good night.
Thank you very much. Maybe over one a little bit.